Oh. Hi, good morning. Welcome to Sheffield. So how many of you here from the Intelligent Systems MSc? Wow, no one from the Intelligent Systems MSc? No. What courses are you from then? Robotics? Yeah, hands up if you're on robotics. Okay, hands up if you're on computer vision. No. Advanced computer science? And advanced software engineering. Very good. Anyone else? Fourth years from undergraduate computer science? Excellent. Very good. Okay, so a nice little mix. The course is about machine learning and, well, the adaptive intelligence. I don't know why we have that in. So what is machine learning? So who can tell me what machine learning is? Anyone? No? Why are you here then? Studying something you don't know what it is? Anyone got a definition of machine learning? Yeah, no? Okay, there's a lot of teaching to do then. So machine learning is currently the mainstay technology underneath what you hear of as artificial intelligence. So in the machine learning community, we've traditionally not used the term artificial intelligence, but every current breakthrough you're hearing about in AI is done via machine learning. So these sort of image recognition things where, you know, Google is trying to recognize features and objects, these weird hallucination things that they're trying to show images of things that look like hallucinations. These are all using machine learning techniques. I mean, so, I don't know, let's have a look at Wikipedia then, since you guys apparently don't know what machine learning is. Machine learning is a subfield of computer science evolved from the study of pattern recognition and computational theory and artificial intelligence. Machine learning explores and studies the construction of algorithms that learn and make predictions from data. I think that's the sort of key thing. So when we formed I was in the community when it sort of adopted the name machine learning. We used to be like the neural networks community, and then we started doing support vector machines in Gaussian processes, not just neural networks. So we sort of became, there was already a pre-existing machine learning community, and that was like about 15 years ago. Now, that's exactly what it is. The idea is that you learn from data and make predictions. So that was in contrast to traditional AI at the time, which was sort of rule-based. So you ask humans about rules, about the way things work, and then you use those rules to try and be intelligent. And that just sort of didn't work because the number of rules that humans have to create in order to, for a complex system, you get an enormous number of rules and performance tends to suffer. So this is the main course text. There should be a few copies in the library. It's Rogers and Girolami, and it's a first course in machine learning. I like this course because I was about to write extensive notes, and you do have quite extensive notes for the course, but I was about to write extensive notes, and then they published this book, and apart from some notational differences that I have with them, I think what they cover is really, to a large extent, what I'm like to cover in this course. Now there's an older book that's Pattern Recognition and Machine Learning, Chris Bishop. This is more comprehensive. It covers more things. It's about 9 years old, but even when it came out, I don't think it was state of the art, but it was aiming to be, 2006. It's still like a text that's used by graduate students, and it has some nice concepts in there. So some of the reading will be from that book, but the other book is the more primary reference. So this is what I think of as machine learning. There's only two things in machine learning. There's data, and then there's models. And then you combine them together to make predictions. You can't make predictions without a model. That's sort of by definition. Like data on its own, so if I say, what's the temperature at this instant, right now, like now, it's a moment before, but now, I can say what the temperature is. If I use that to predict the temperature in the next second, I'd probably say, well, the temperature would be the same, right? So you think you're being model-free. Well, you're not being model-free because you're assuming that temperature stays the same. I mean, just because that happens to be true, that's, that temperatures don't fluctuate in a room like this extremely quickly. That's still a model. I mean, you would be very surprised if I were to disappear from here and reappear on the other side of the screen instantaneously, right? Now, although you think that that's true, that won't happen, Of course, if you go down to very low levels in quantum mechanics, these sort of things can happen. So it's at these high levels that these things don't happen, and you have a model of the way I'll move. You don't actually have an innate understanding of the physics. You've just observed over time that these things don't happen. So like a really strong assumption that we use a lot is what I've just said. It's sort of a continuity assumption, or we would more commonly call it smoothness. So that if we see some piece of data and then we see some other, well, we want to make a prediction close to that data, in some sense, where I haven't really defined what close is. Then we say, okay, if it's going to be similar to the other data we've seen that's close to. But that's a model, right? That's not true in a mathematical sense. That's a prediction. It could be, and indeed there are circumstances where you see massive fluctuations. So if you have the data on its own, if you have a time series of temperatures, even if you think, oh, these temperatures look really, let me see if there's spotlights. Cool, that would be cool. Oh, that's impressive. Spotlights, this one. We have lights on the front somewhere. Hopefully that'll come. Oh, that's just because of that. Try and get these up. No. So one. Okay. So just because I give you sort of, that's a great start. Temperatures over time in a sequence. So here's some data you might have. So that's not a great one either. There's quite a lot of them in here, so we could do this for a while. Okay, still not great, is it? How about blue? You get rainbow axes. It's just this board, I think, is a bit odd. Okay, let's try black, because it's likely to be the easiest to see. Okay, so, it's not the easiest to see at all. Okay, let's go back to blue. So let's assume that we've got some temperatures over time that we're observing like this. Now you're all thinking, oh, well, the curve fits through that. You kind of don't really have any right to make that statement without a model. Like if you don't know, so what you're sort of saying is that the temperature is a function of time. And then you're assuming when you look at that, you think, oh, some curve like this would fit to it. But that's a model that you have to do that. And once you have that model, you can make predictions at other times. I mean, you can't even necessarily make a prediction for what the temperature would be at this time if you measured it again, because your sensor might be noisy. Yeah? So you might, even if you've seen it, all you can say is at that instant when I made that measurement at that point in time, that's the data I got. If you were to revisit that measurement, you might get a different measurement. Or if someone else were to make a measurement with a different sensor, they might get something different. So all these sort of things require a model to make the prediction. And I think models are at the heart of machine learning, which is why I emphasize it so much. So what is data? Well, data are observations. That's what we input about the world. Sort of almost everything can be turned into data. Text, images, the temperature in this room, the color of my top, can be all turned into data. That's all data. So data, etymologically, it means that which we're given. So it comes from Latin. And in French, actually, it's even donné. As it's like directly in French, the word is given. So the things we are given, so I'm just thinking about plugging my laptop in. I don't have a spare plug, though. The things that we are given in order to do our predictions. So you can sort of think of, it's sort of hard. I was asked a question. I was phoned up by there's a lot of excitement in machine learning recently. So I was phoned up by a journalist and asked if I could describe what data was. And I kind of said, well, everything's data. It's all, I can't think of what's not data. It's like this, I find that even you could even represent a model as data. You could even turn a model into data that you give to someone else and model the model, with some other modeling system. You can turn everything into data. But normally we think of it as numbers, right? Normally we actually have vectors or some sort of input, some mathematical number. It doesn't have to be a number. It could be a structure or something else. And this model contains our assumptions, and they're based on previous experience, which might be other data, things we've seen before. Or there's a process known as transfer learning. So like, for example, if I learn to walk, then what does that tell me about learning to run? So you can sort of develop a model about walking, and then you try and take that model and move it to the area of running. We're not going to look at transfer learning in the course, but it's an area people are very interested in. But I kind of think, at the extreme, what it means is it's our beliefs about the regularities of the universe. It's how we see, things operating in the universe. Now, it's not, okay, so you think, well, that's physics. Well, no, because often we don't go into that detail. You do a lot of prediction. You didn't have to learn physics to sort of make predictions as a kid, right? You didn't have to know Newton's laws to catch a ball, right? It's just you have a model about the way the ball's likely to move, and you put your hand out and you catch it. A lot of it's subconscious. Now, in cognitive science or psychology, this would be called inductive bias. So inductive bias are sort of like your prior beliefs that you bring with your brain to look at things. And in machine learning, we're often inspired by looking at how humans think. Indeed, that could be the main, for me, that's the main difference between machine learning and statistics. So statistics is about analysis of data to try and find out the truth underlying the data. Machine learning typically is more about trying to get computers to do the sort of things that humans typically do well. Right, so that doesn't necessarily mean we're looking for truth. We're just looking to sort of replicate or do something effectively. There's some other differences, but a lot of the methodologies end up being the same. So prediction is the action to be taken, a categorization or a quality score. So a prediction is, so I say the word, I'm saying, okay, Google, navigate to Regent Court on my phone, right? And that's all done by machine learning. What happens next? Well, it sent up the network, it's processed by Google's servers by machine learning, and they combine the data, which is in that case my speech, with a model, which in that case is nowadays a neural network, deep neural network model, and they make a prediction, and their prediction is what I actually said. And their prediction is their guess of what I said, given the sounds they've had. Any questions at that point? Yes, no? Okay. So let's think about a simple data, so fitting data. Now we're going to, in this course, use Python. We're going to use the Jupyter Notebook. This used to be called the IPython Notebook, so you'll sometimes see it referred to as IPython, but it's nowadays its official name is the Jupyter Notebook. We're using the Jupyter Notebook, and I'm doing this presentation for the first time in the Jupyter Notebook, which is why it might be a bit flaky at times, because it's really a state-of-the-art tool for doing data analysis and scientific computing. We are right at the forefront. So if I go to jupyter.org, so it's an open source interactive data science and scientific computing across 40 programming languages, is what it says. It's a very nice recent site that's set up very nicely. And if we go down and we look at what it says about the Jupyter Notebook, it's a web application that allows you to create and share documents that contain live code, equations, visualizations, and explanatory text. Uses include data cleaning, transformation, numerical simulations, statistical modeling, machine learning, and much more. Now, share documents that include live code, equations, visualizations, and explanatory text. That's pretty much everything we want for machine learning. It's a wonderful tool. And we've been very active. So you can choose different languages. We're going to be using Python. I'd like to make you more use of these interactive widgets. We do use them a little bit in the second thing. Now, because we're using a tool that is state-of-the-art, this is evolving very quickly, and this does cause us slight problems because there's things we have like from last year that will not work this year because it's moving quite quickly. But that's a choice we make. We could either give you like old ways of doing things and be certain that they'll all work, or we can give you state-of-the-art, and then occasionally we'll hit little bumps, like I was hitting earlier trying to get the slides up, which is why I started slightly late. So, and this is quite nice. I like that. Look at that. Currently in use at Google, Microsoft, IBM, Bloomberg, O'Reilly, the books. Continuum Analytics is like, I think they're one of the makers of Python spaces. Some other companies. Berkeley, the University of Sheffield. George Washington University, Northwestern University, NYU. So we're quite close to these guys who are creating it, but it's becoming a real international phenomenon. I mean, it's getting a lot of funding to do this sort of thing. And the reason is because of things like this, what I'm about to show you. So you can have a document, which in this case is a slide presentation. You can have a bit of code in it. So this is Python code, and what we're going to be using is NumPy. So NumPy is a library in Python. which we can use for numerical computing. Python was not written as a language for numerical computing. It was written as a scripting language for processing text and things like that. So the numerical computing comes later. Now, this means that sometimes the syntax is a bit ugly. So if we were doing something like MATLAB, then we would have x is equal to create a vector. You may have seen MATLAB before. Who's seen MATLAB before? Yeah? So that would be the MATLAB syntax. And actually there's a language called Julia which has a very similar syntax. And you can use MATLAB in the notebook, you can use Julia in the notebook. Here you've got this slightly ugly thing where this thing here in Python would be a list. So what these things are doing is they're converting lists into arrays. So the difference between a list and an array is, how it stores the data. So an array contains typically the same types of objects. So actually, in fact, what we should strictly do is this: have dots to show its floating point numbers. That's a real gotcha in Python. If you can end up creating arrays of integers, and then you do integer division, and that's a bit confusing. So if I run that, then it's all we've done is we've created an array called I've just deleted it. See, there you go. I told you there's I was trying to create a new one below. Let's just go out. So this is the notebook itself, which I've been using to and then what you can do is you sort of insert cells. And so this is a code cell, the one we've just been showing. And in this code cell, what did I have? I had import numpy as np, and then I had x equals np.array, I think, was it 1,3, 1.3, and then below I had y equals np.array 3.1. Now, the advantage of that is now I can actually look at what those things are. So I can do print x, and there's the little array. And I can do little things like x times y, and that's just 3, 3, because that's an array multiplication. Let's just get it back to the slideshow. So this is what we just had in the slideshow, yeah? So let's see if I can actually delete it now. Oh yeah, it worked that time. Now the model we're going to look at here, this is data. So what this is saying is that we've got two data points. Data point 1 says that we have an observation at x1. And well, Python indexes from 0, so this annoyingly is x0. It's not. I prefer indexing from 0, but in maths we tend to index from 1, so that'll be something that comes up a bit. x1 is 1, and x2 is 3, and y1 is 3, and y2 is 1. And what we want to do is fit a model, and here's a model you should all have seen before. A model would say there's a linear relationship between these two. And this model works very nicely. So we can actually find out the parameters of this model quite easily by an equation like this. This says that the gradient of the model, m, is equal to the difference in y2, delta y2, over delta y1, and then that the offset is given by computing the value of sort of feeding m into the equation and reorganizing, because y equals mx plus c, so we put the plus x on the other side and we get y. So two unknowns, m and c, and two observations. And we're done. So we can do that, and we can implement the result in Python. So what this line does is it creates a linearly spaced array with only two values. So it's actually just 0 and 5. And then I'm implementing this equation here. Yeah? Because Python indexes from 0, it's y0, not 1. And c. Yeah? And then I'm making a prediction. So these new values where xvals is my input, I sometimes call them something like that as x test. I'm making a new prediction of what y is. So if I run that little bit of code, I've got the data in already from the previous slide, and that's going to make a prediction. Now, what I can show you is what that prediction looks like. So this is actually that fit. Sorry, it's got my shoelace undone. I'll end up tripping across the... So this is actually a plot of that fit. It's not a very interesting plot, but it's got two things. It's got that gradient m and that offset c, which we computed. And there's the data that we had. So the line goes straight through the data. So this is very good. We can combine our model with data, and we can make a prediction. What might be the problem with what we're doing? There's just the right amount of data. If we had any more data, we'd be in trouble, and any less.
It might not be linear.
Might not be linear, yeah. There's lots of... so we all do want more data, but actually, oddly, in this circumstance, I want to take you right back to sort of things you probably don't think about much. What if we get a third data point? So in a third data point scenario, there's now 3 different lines, none of which fits those original, well, all 3 points. So you actually end up with a choice of lines. So if you get more data, you actually end up with a family of different solutions under this. So how do we resolve this? So there's known ways of resolving this. You'll have studied ways of resolving this, but you probably won't have thought about them in the way I'm about to sort of introduce them to you. So do people know, like, I mean, how would you do that, like if you're doing an experiment at school and you're supposed to do a fit of a straight line to some data? People remember how you do that? We're going to do it in the next lab, actually. We've got a lab on it. But I want to justify that for you. So how would we do that? We've got 3 points. We've got to fit a line. In effect, what we've got is an overdetermined system. So that was the original data, 2 simultaneous equations, 2 unknowns. Yeah? But now I went and added, it's actually not this data point, it's something slightly different. I added this data point. And that's blown everything apart. So do people know what this is called when you have this situation? Pardon? It's not overfitting. No, over is correct, but it's not overfitting. We'll come to overfitting in a few lectures' time. But it's over is correct. It's over something else. It's an overdetermined system. So we've got more sort of we've got more... fewer equations than we have, more equations than we have unknowns, right? So you can't solve these sort of systems. They don't solve. They can't be solved exactly. You know, that implies that's not true, okay? So this actually, you're not the first to sort of like, this is my way of introducing machine learning, and I like it because you're not the first to sort of wonder, well, what does one do about that? So any thoughts about what and how you could deal with that? So least squares fitting, yeah. So least squares fitting is something people do. But I think when people say least squares fitting, it's like, it's just something you're taught. You're not taught the whys and wherefores and what it means. So it's exactly what you would do, is you do least squares fitting. But what I want to do is step back a little bit from that least squares fitting. And we're going to do that next time. So next week, we're going to do a lab class where we just fit objective functions by least squares. What I want to introduce you to is this gentleman. Do you know who this is? He looks good, doesn't he? He was about, I don't know, he died when he was 80-something, so he may have been in his 70s or 60s there, I don't know. This is Pierre Simon Laplace. Laplace. Now, I think he's one of the most, for me, he's the most interesting mathematician, scientist in history. And he writes about, unfortunately this is a bit small, let's see if we can zoom it in. So who speaks French? Anyone here speak French? Good, I can do a terrible accent then. It says, nous devons donc envisager la tête présente dans l'univers comme le fait de son état antérieur et comme la cause de celui qui le suivre. Look at this. So this is saying, I think we must now look at the present state of the universe as the effect of the previous state and the cause of that follows. And then it says, une intelligence qui, pour un instant donné, connaîtrait toutes les forces dont la nature est animée, an intelligence that, for an instant given all the forces by which nature is animated, and the respective situations of their composition. Oh, well, it's actually a little bit easier if we just look at the English translation. We ought then to regard the present state of the universe as the effect of its anterior state and the cause of the one which follows, which is to follow. Given for one instant an intelligence which could comprehend all the forces by which nature is animated and the respective situation of the beings who compose it, an intelligence sufficiently vast to submit these data to analysis, it would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present to its eyes. And then it says, the human mind offers, in the perfection which it has been able to give to astronomy, a feeble idea of this intelligence. And then it goes on to talk about discoveries. This is 1814, he's written this. And if you see what he's written, so this actually, does people know what this is? We ought then to regard the present state of the universe as the effect of its anterior state and as the cause of the one which is to follow. Do people know what that's called? That's an assumption. Pardon? This is called Laplace's determinism, yes. But but just on that particular point, the whole thing's called determinism. But on that particular point, what's that property that the present state is the effect of its anterior state and the cause of the one which follows? Have people heard the Markov property? So this is the Markov property. And actually Markov is like, I don't know, 100 years later, 60, 70 years later. But Laplace is talking about this property here. And then he sort of says, given for one instant an intelligence that could comprehend all the forces by which nature is animated, so understands all of physics, and the respective situation of the beings who compose it, so that means like all the state variables, that means all the data, right? An intelligence sufficiently vast to submit these data to analysis, that's computational. So it's saying you've got full knowledge and you've got computational, so full knowledge means like massive memory. I mean, he wouldn't phrase it in that term, he didn't have computers. And then he's talking about the computational requirements you would have to have. And then it can say, for it nothing would be uncertain, and the future as the past would be present in its eyes. So the funny thing about this is people call this Laplace's determinism, and they go on about it as if, as if Laplace was some kind of moron or something. And it actually leads to this idea of the deterministic universe, which is greatly discussed in philosophy. And in fact, if you go to the Wikipedia article on it, it's called Laplace's Demon, first published articulation of causal or scientific determinism. According to determinism, blah, 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 blah. Goes on and on. Well, this essay was actually called a philosophical essay on probabilities. So don't you think it's rather odd that Laplace is defining determinism at the beginning of a philosophical essay on probabilities? It is odd. And the reason it's odd is because he's defining it as a straw man. He goes on to say, don't be so stupid. Nothing could ever exist. So the next thing that Laplace says, and I find it really irritating, look at all this stuff. All about arguments against, I mean, it's Laplace's demon, arguments against. He goes on to say this doesn't happen, like on the next page. Always check your sources. So on the next page, what he says is, he's talking about the planets, because this is what they've done good predictive stuff on in that time. The curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. So what he is saying is that you will not be in that situation. There will always be unknown things, and we use probability to deal with it. So the ironic thing about Laplace's determinism, this is page 6, right, of the book. So you only have to go into page 6 to get past the bit. So this would be page 4. You have to read 2 pages later to find that Laplace is saying that this is not the way of it. That actually, in fact, what we have is, let me just zoom back out again. What we have in practice is probability. So this was Laplace's solution, and he was, as far as I'm aware, the person to suggest this solution. He's not famous for least squares. Him writing these down, this solution, predates least squares, actually. He's not famous for the most common way of doing this, which is named after Gauss, who was a follower of Laplace. But philosophically, this is what he said. The way to deal with this situation is to add, so we might today call these slack variables, but you could also call them noise, but you could also just think of them as the way in which the model is departing from the real world. So what Laplace says is you have a model, you will not predict what's going on in the real world because of your ignorance. And your ignorance of what's really going on. Your model is an abstraction, it's a simplification. It does not take into account, when Laplace was interested, he was looking at the stars and he was measuring them with telescopes, and the atmosphere moves and all these sort of things, and that's not in his model. His model is that there's just gravity or Kepler's laws and planets move around in a fairly deterministic way. But then when he was also, the thing about Laplace is he was an earlier sort of studier of probability. So he did this work on the planets, but he also did work on gambling. So he is the one that synthesized these two ideas to say, well, that probability that we have for rolling of dice and these sort of things is also necessary here. And what we need to say that our observation is equal to what's in our model, which is y is 1 here, which is y, so there's a 1 there, plus some corruption. What's in our model plus some corruption. What's in our model plus some corruption. And you don't know what that corruption is. Now, Laplace then spent a lot of time trying to derive what this corruption would be from first principles. So he tried to sort of come up with formula for a good distribution, and that's actually pretty hard, because certainly in these regression cases, the corruption in theory could cover the entire real line. It could be anywhere between infinity and minus infinity, and so you have to define probability distributions over that space, which we're not going to look at today. I think we may look at them a little bit tomorrow. But so he spent a lot of time coming up with quite complex probability distributions to do this. Least squares comes later, and we'll see that in lecture 3. So least squares is Gauss chose the Gaussian distribution. He didn't choose it because it was named the Gaussian, because it wasn't. In fact, Laplace invented the Gaussian distribution, and you'll see in the notes there's the Gauss credits Laplace with the Gaussian density, but he didn't invent it for this. So Gauss was the first person to take the Gaussian distribution and use it for these variables, which is why it's known as the Gaussian distribution. And that's what leads to least squares if you use the Gaussian, as we'll find out. So probability is very important. It's very, very important to us. The things you will need to know in this course are probability, linear algebra, and a bit of matrix calculus. So matrix calculus is multivariate calculus, sort of differentiation done on matrices and vectors. Now in the notes, and if you go ahead and look ahead in the notes, you'll see that we've got quite extensive material. So who here is on GitHub? 1, 2, 3, 4, 5. Who here knows what GitHub is? I mean, obviously those, yeah. So 6, 7. I mean, the ones who were on GitHub just put their hands down. So I'm assuming they know what GitHub is. But so who else doesn't? So who doesn't know what GitHub is then? Okay. So GitHub is how we're going to distribute the notes. And if you've used Mol before, you'll be very grateful that that's the way we're doing it. So I provide links somewhere for this, I think from my webpage. So these are the slides in the notebook, and this is today's lab class. So actually the nice thing about this is GitHub it's a version control system. But the really nice thing about it now is it actually renders the notebook. So this is an IPython notebook that you use in the lab class today. And it's going to be a bit of a probability review. Now what we're going to do is you are going to go through these notebooks, and what you'll see is that there's questions. And then there's a box for you to write your answer. So what we're going to do is we're going to have 10% of your course every week is going to be on these lab classes. So this one is an introduction, so you'll see that this is, look, who invented Python and why? It's just to make you go and poke around and find out a bit about Python, and is it an object-oriented language? Because not everyone will be familiar with Python. So it's just a familiarization session today with some marks for the familiarization. So you should be looking to get a good number of marks on this one, and also to get used to the system. Because what we'll do is you'll submit this notebook before 9 o'clock next week. Yeah. So this time next week, you have to have submitted this notebook. So your aim should be to get through a lot of it in class. If you're not getting through the whole thing, I mean, this applies less today than it will in other weeks, ask questions about the questions that are coming up. Make sure you look ahead and get the support. And then in your own time, you finish the notebook. Now, the reason I do this is because what I was finding is if I just set an exam, people weren't covering the material. And this is a way of sort of making sure people go through all the material. And most of these notebooks have a fair amount of background stuff as well. So stuff that is in your prerequisites. But I always find, so your prerequisites for this is you're supposed to know linear algebra. And it's surprising that in practice, people last looked at linear algebra in their first years or something and never thought it was useful for anything. So kind of have forgotten it by now. So this session here, which is coming on the 13th of October, is... It's going to review next week's session at the start. That's a review of next week's session. And then, oh look, spelling error. And then it's going to introduce linear algebra by introducing linear regression. So it's going to try and persuade you of the importance of linear algebra algorithmically. So you're going to start off doing some differentiation, some fitting of data. So this is linear regression. Look, here you've got some little things in here. So this is the sort of things that I want you to get used to in the assignment. These are the things that are useful in machine learning and practice. So we're going to use LaTeX for sort of doing little bits of math. So I'm asking you to write down the LaTeX equivalent of these commands. Little things like that, which just stop and make you think. Then, of course, as you get towards the end, you get some questions which are... write code for your answer to this question, initialize this, it's giving you a sort of task to do to fit a linear regression. So you're doing some work in practice. And then it introduces linear algebra. Now when it does introduce linear algebra, it does so reasonably slowly, right? So you're supposed to sort of know this stuff already. But what I'm trying to do with this stuff is persuade you that it's of its utility and introduce it in particular ways. Gauss and Laplace didn't have linear algebra. And we've got some examples in here, which you'll see in the class, where these commands here, I'm hoping pods is working. So this thing pods is a thing I've written to help with the class. And we're going to check that it's working in a bit in the lab class. And this thing here displays a book from Google Books. And the book it's displaying is Laplace's book on philosophical essay on probabilities. So what it's not actually, it's Legendre's book on least squares. So it's Legendre's paper when he first introduces least squares. He doesn't use linear algebra, and it's a lot more complicated. So there'll be a few things that I'll expect you to know. And one of them is probability. So there's a bit of probability review in the end of the slides here. Probability is pretty simple. And we'll just spend a couple of minutes just reviewing what it involves. Now, there's three different types of probabilities we care about. The joint probability. So here, x and y are two events. And this is the probability of x, the event x, the result of the event x, which might be, I don't know, the temperature on Tuesday, being equal to x, small little x, where little x is a number. It could be like 20. And then this is the joint probability of, I don't know, the amount of rainfall, where little y is the amount of, big Y represents the amount of rainfall and little y would represent 20 millimeters. So that's the joint probability of those two things happening together. So where you read that, when you see that notation, there's a probability that the temperature equals 20 degrees and the amount of rainfall is equal to 3 millimeters. The marginal probability, the way you read that, is the probability that, so marginal, it means, why do we call it marginal? Well, this has sort of disappeared. It's still there, but it's disappeared. So we can think of it going into the margins, right? So it's a marginalization is the removal of a variable. So this variable really exists. It's not that the rainfall disappears when we talk about the temperature on Tuesday alone. But if we don't want to know the relationship between the two, then we say it's the marginal probability. And that's the probability that the temperature is 20 degrees regardless of the amount of rainfall. And regardless of anything else, regardless of the colour hat you're wearing and whether England lost to Wales in the rugby. The conditional distribution here is the probability of the temperature being 20 degrees given that the rainfall is 3 millimeters. So this actually starts being a bit like machine learning because these are the givens or the data. So this is something that you'll see coming up as we go forward, is that this is like a prediction, the probability distribution over the temperature on Tuesday, given that we know it's rained. And for me, that's the whole of machine learning just there. That's how it should be done. That's not how it is all done. But because it gets complicated with probability. But for me, that's really what machine learning involves. That prediction of that given some information. But it's the conditional probability, so it's the probability of the temperature equaling 20 degrees given that the rainfall is equal to 3 millimeters. Now there's a little bit of review here which you can sort of flick through in your own time, but it's just trying to persuade you that, like, so with a joint distribution here, so these might be leaves falling on a grid. So let's say we go out on St. George's and we put out like a grid, square grid, and we watch the leaves fall because it's September. And then we carefully mark where each leaf fell. And then we discretize, because we haven't looked at continuous probabilities. So we sort of say falling up to 1 to 6 meters from the tree. So this is where the tree is, and these are where the leaves fall. I don't know, all the branches here are dead or something. So there seems to be one branch, and all the leaves seem to be falling in this region here, or maybe it was very windy. So the way we define these probabilities, so this is across the x and y direction here. This object here, if we count the number of leaves that fall in this object, we're calling that nx equals 5. So that's the number of leaves that fall in x equals 5. If we count the number of leaves that fall in here, that's the number of leaves that fall in y equals 4, regardless of the x direction, regardless of the y direction. And this thing here is the number of leaves fall in the area that x is 3 and y is equal to 4. So those three things are enough to start allowing us to look at the definitions of these probability distributions. So the joint probability is that number of x and 3 and y equals 4 divided by the total number of leaves in the limit as the number of leaves go to infinity. That's called the frequentist definition of probability. Actually, most of the time we won't use the frequentist definition, but it's consistent with the definition that we'd use, which would be a so-called Bayesian definition. But that's sort of what you can think of. Conceptually, that's what you can think of as a probability distribution meaning. The marginal probability is the number that fall in that single x slot divided by the total number. So that was all the row across x. And the conditional probability is the number that fall in that single x, the number that fall in that single x comma y slot divided by the marginal for y. So just going back again, looking at that. The joint distribution is the number that fall in here divided by the total. The marginal distribution for x is the number that fall in here divided by the total. The conditional distribution of x given y is the number that fall in here divided by that number, because we're given that number. That's the conditioning number. Yeah? Okay? So conceptually we have that, and that means it becomes very easy to compute. So just a bit of notational detail. We don't normally write this, right? Because it's a bit of a pain. We often use this. Who's coded in Python before? Okay, so as you code in Python, as you go on, you'll know that you use arguments where you say, what's called? It's named arguments, isn't it, right? So in C and other languages, the order of the arguments matters. Probabilities like Python, in effect, has these named arguments. Here, there's an implicitness that these named arguments are here, but the ordering still doesn't matter. That's very important to remember. So P of x comma y is equal to P of y given x. People are not used to that because for a regular function, it's like a C function, the ordering does matter. Yeah? So this is just a notational thing. So that for a function C, that's what that's saying. But this does equal this, because effectively this. So the rules of probability, though, can easily be sort of derived by substituting in the definitions. So all distributions are normalized. So this is clear because whatever's on here, the sum over whatever's on here must always equal the bottom. So a distribution's always sum to 1 if you look at all the possible states of the distribution. The sum rule says that the marginal probability, which is of that form from our plot before, is related to the joint distribution in this way. This is the rule. You need these rules. They're very, very important. It's a very complex rule. It's called adding, right? So it doesn't involve anything more than adding across a thing. It turns out that this is often one of the most difficult things to do, and this is the bane of our lives, even though it's just adding, because the state space over which you have to add tends to be very, very large. So this is, we'll be integrating in continuous cases, doing adding in discrete cases, but this is the sum rule of probability, and it allows you to go from this joint distribution to the marginal distribution. You're just summing over the state variable x to get rid of x. So that's the process of marginalization that's normally known as. The product rule allows you to go from the joint to a decomposition of this conditional times the marginal. So it's written out here just to persuade you, look, you can cancel these two things here. These are just those limit definitions we used before, and then you get nxy over n, right? I'm not really going to ask you to prove this sort of stuff. I just want you to remember it. But this is just a sort of little persuasive thing that's how it works out. But this is the thing I want you to remember. These are the only two rules of probability, really. Multiplication and adding. It's easy, isn't it? So multiplication is, so the conditional of x given y multiplied by p of y, the marginal of y, gives us the joint distribution of x and y. And that's really, 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 really useful because together those two are called Bayes' rule. But it's not even a rule. It's just being able to divide by stuff. Right? It's just really, I kind of get irritated by how much emphasis is put on this thing. It's not a complex thing. That is the joint distribution, and because the arguments swap, that's the joint distribution. Now, you could express this joint distribution as p of x given y comma p of y, or p of y given x times p of x. That's just the product rule being applied. Now, if we divide both sides by p of y, wow, it's a new rule involving dividing. So p of y given x is equal to p of x given y times p of y divided by p of x. Sorry, I divided by p of y mentally because I wasn't looking at the board. But either way it works. This is interesting because let's say you often end up defining the model here. So you want to know something about y given x, but you have a model of x given y. And so you use Bayes' rule to invert those things. Now there's a little bit more stuff for you to do if you're not familiar with these things in your spare time. There's Bayes' theorem example in the notes. There's some reading to do. There's expectations that I don't think we need for this afternoon. So computing expectations, which you don't have time to do now. And then there's some reading at the end. So I'll get these slides back into GitHub. But if you go to my webpage, so if you search for me, I should come up. I come up for me, that's because I vanity search all the time. So let's see, teaching on the top here. So that's our thing, MLAI 2015, inverseprobability.com, MLAI 2015. So what you'll see if you go to these things is you've got week 1 at the top here. Now what you'll find at the moment is that you get a PDF copy of their slides because I'm creating these new slides on the fly, okay? But it's the same content, but it's PDF, okay? So that may be actually even easier for you to look through. And there's some examples to look through. So I think we're back at 11 o'clock up the top there. Do people know where the lab class is? It's FF 104, yeah? And so I'll see you at, sorry, not 10 o'clock, 11 o'clock, okay? Great. So when we go to the lab, I'll show you how to download the notebook. Just a bit of patience in the lab because we'll find that all sorts of things probably have some niggling problems due to last year's changes and whatever. Hi.